Hello everybody. So let me show you how to solve this problem about maximizing the size of a rectangle inscribed in a semicircle. Okay, so I might imagine the situation like this. I've noticed that this problem did not come with any kind of diagram to go along with the explanation. So I've drawn it, and I noticed that it says that the diameter, or sorry, the radius of the semicircle is 13. Okay, so here I've drawn a semicircle, a half circle, all right, and it has x-intercepts at 13 and negative 13. That would make the radius 13. Okay, from this origin point there is 13 units, and from the origin point there is 13 units. And if I had labeled the top one right there, it would be 13 units up. Okay, so what I'm looking at here is definitely a semicircle of radius 13. In red there, you see I've drawn the rectangle that's inscribed inside of it, okay? All right. Now, there are lots of ways I could have drawn that. I could have drawn it taller and narrower, wider and shorter. There's many ways that this rectangle or any rectangle can be inscribed inside this semicircle, okay? But I want to know how can this be the biggest, okay? There's one way that's bigger than every other possible way. All right, so let's think about it like this. Here I've drawn the semicircle and the rectangle on the XY plane. I didn't label the X and Y axes when I drew this, but this is the X axis and this is the Y axis, okay? And I do that in order to get equations that I can work with by way of doing calculus, all right? So here's what I'll need to do. I'll need to, with this information, somehow get a formula for the area of this rectangle, because that's the thing that I'm working with. The question is based on me maximizing that. So here's how I do that. I noticed that as this rectangle is inscribed in this semicircle, one of the or both of the corners hit the semicircle, okay? And if I could tell you where the corner hit the semicircle, I would get an x coordinate and a y coordinate. The y coordinate would be how tall the rectangle is. And if I double the x coordinate, that would be how wide the rectangle was. And if I know those, then I know the area, because the area of the rectangle is the product of the sides. So how do I do that? I need an equation for the semicircle, because if I have an equation for it, I can tell you the x and y coordinates, okay? So let's pause right there. Let's talk about circles. So in general, if I want the equation of a circle of whatever radius with a center at the origin, it's going to be x squared plus y squared equals the radius squared. That's the equation for a circle with center at 0 and 0, which is the origin, radius of r. If in this problem I'm dealing with a semicircle of radius 13, then I might start like this. I might say, okay, if I have a circle of radius 13, center at the origin, that equation is going to be x squared plus y squared equals 13 squared, okay? Or x squared plus y squared equals 169, which is 13 squared. But that's an entire circle. So how do I talk about, like I have it right here, just the upper portion of this entire circle, which would give you a semicircle, and would be what I have in my picture. You solve this for y in terms of the positive square root. That's how you do it. So if x squared plus y squared equals 169 is the entire circle of radius 13, then y equals square root of 169 minus x squared. What you get when you solve this for y with a positive root is going to be just the upper portion, just the semicircle that you see here, okay? So then that point has an x coordinate of x, and it has a y coordinate of root 169 minus x squared. So here's your x and the y coordinate for that corner point, okay? So that's why I say that for this rectangle, in general, it will be like this. The width will be double the x, and the height will be root 169 minus x squared, okay? It's going to be like that. Now, what x is, who knows? Like, x could be 1, and it'd be a relatively tall but narrow rectangle. X could be 12, it'd be very wide, and so on. There's lots of ways it could be, but it's all based on the x, Okay. All right. Why do I say that the width is double the x? Well, because the x coordinate means from the origin I go right x. But that's only half of the width of the rectangle, as you can see. So double it to get the entire width. Okay. So what this will come down to in terms of maximizing the area is maximizing this function. This function is the area of that rectangle. 2x times square root of 169 minus x squared. Okay. So how can we do that? If this is our function that tracks the area of the unlimited number of rectangles that can be inside this circle, how do I find the one that is the biggest through that function? Right here, this tells me the area, it tracks the area of every possibility, which one's biggest. If I solve a prime is 0, if I take the derivative of this and set it equal to 0 and solve it, that will take me to my answer. Okay? So let's say part 1. Now I'm dividing this into parts. Somebody else might divide it up slightly differently, but this is how I'm doing it. But these parts have all the elements of the problem. I need to find the derivative. So if this is the area function from here, then I need to find its derivative, and I would use the product rule and the chain rule together. Okay? So that's what you see here. I've labeled it. I've given you the product rule with the same labeling. The chain rule is involved right here, okay? And then with a little simplifying, I get this derivative. All right, so there's your derivative. Now, what I said from the beginning is no matter how I divide these parts up, finding the maximum area will come down to solving the derivative of this for 0. So naturally then, if I just found the derivative, part 2 will be solving it for 0. So if I take this and set it equal to 0, moving this negative term to the right will get you this equation. And then multiplying both sides of that equation by 169 minus x squared to the half power in order to cancel this fraction will get you this equation. Then I do some distributing, combining like terms, dividing by 4, simplifying, and I get x squared is 169 over 2. Solving for x, I get x is root 13 over 2. Square root of 169 is 13. Square root of 2 is square root of 2. Okay? All right, so that's the key to the answer. Do you know where this point has to be for this rectangle to be bigger than every other possibility? That point right there where that corner is has to have an x coordinate of 13 over root 2. Okay? Now, let's pause here and see, like, well, what did it ask me? Okay, did it ask me what the area should be? Did it ask me what the base and the height were? Because I guess if the question is to maximize this rectangle, it could say, what's the maximum area? What's the base? What's the height? Any of those questions are fair. The question, though, is what is the base and height of the rectangle with maximum area? Okay, so let's do this. If x is 13 over root 2, what's double x, which is the base? Okay, what's twice 13 over root 2? 26 over root 2. So the base is 26 over root 2. Okay, and what's the height? Okay, so if x is 13 over root 2, the height is root 169 minus x squared. So if I'm going to tell you the height, I'll take this number, 13 over root 2, I'll plug it in right there, root 169 minus x squared, and that will be the height. That turns out to be 13 over root 2. Okay, so then I can take this number, which is not the answer. Okay, this holds the key to the answer, but normally when we solve the derivative for 0, it does not just tell us what we want to know. There's some interpretation that goes on beyond that, and that is here and here. Use the x to find the base and the height. Okay, and then they go like that. All right, so that's how we solve this one. Now, at that point, I'm done solving this, but there is something I should mention just for the larger curriculum. We use the second derivative to know if the point is truly a maximum or a minimum. Okay, so in this case, I wanted to maximize the area. Okay, and I got this solution. This number on its own doesn't really prove anything. It could be that I've misunderstood this question, or I've solved it the wrong way, or who knows. And this number, although it makes the derivative 0, doesn't actually take me to a maximum. So if I was going to verify, now this is just for the bigger curriculum of our class. Before we got to this lesson, we learned about the second derivative and whether a curve was concave up or down. So I just want you to think about this in that context. What would it take to verify that that answer that we got actually produces a maximum area? Should we prove that the curve is concave up or concave down? Well, think about it. At a maximum, the curve would have to be concave down. Okay? That's the only way that there's going to be a point at the top above the ones on either side of it. Okay? So if I wanted to prove somehow that this point does produce a maximum, I need to show you that the curve is concave down at that spot. All right. What would that involve in terms of the second derivative? That the second derivative at that critical point is less than 0. Same thing as being concave down there. So if it came down to it, I mean, it's not an objective of this question, but it could be on some others, so I'll mention it now. If it came down to verifying our critical point, our solution did in fact produce a maximum, I would show that the second derivative at that point was negative, which would be the same thing as showing that it was concave down. Okay, so that's the whole solution. I hope the picture helps you. I notice on many of these in the lesson there's no picture. If that helps you, great. If it helps you to draw it, even better. But it might really get your thinking in order for all the aspects of the problem that you need to know that must come together.